Hello, welcome everyone. In this video, I'm going to work on instantaneous rate of change. Okay, I kind of like show you how average rate of change is converted to instantaneous rate of change and how this is going to play a very important role later on when we learn about the derivative of a function. Okay, so this is just like, a precursor or the beginning point, to a derivative of a function. So let's start with a graph. I'm just gonna continue what we had started. So I don't have great drawing skills. So this is our function, and we have 2 points on this function right here. Okay. Actually, for the simplicity, I'm gonna make the values to be positive. So let me redraw the whole thing. Here we go. So we have 1 point here where our one x value and one x value is right here. Okay. So the first x value is just x, and the second x value is x plus h, which is h units away from x plus h. Okay. And the corresponding y value for this x is f of x, the function value at x equals x, and the y value for this is function value of x plus h. Okay, so this represents the y value of the function at x equals x plus h. Okay, so this is gonna be our first x value, so it's going to be x1. This is our second x value, this is x2. This is our first y value, so this is y1. This is y2, our second y value. Okay, so as we did before, if we want to find the rate of change over the interval, which is the average rate of change, we basically have this, we're going to have this line, linear line connecting. So we have something like that, just a straight line right here. This linear line that connects these 2 points, the slope of this line represents the average rate of change over this interval for this function. Okay, so that's what we had found out previously. So m equals change in y over change in x, which is equal to y2 minus y1 over x2 minus x1. And then we go ahead and make a substitution like we did before. So the slope, which is the average rate of change for this particular line, this is the slope of this line. That's what we're trying to recalculate. So y2 is f of x plus h minus f of x divided by the y2, x2 is x plus h minus x1 is just x. So we go ahead and simplify this. So we have f of x plus h minus f of x. So this is basically the change in y on top, and this is the bottom. We simplify this. This x cancel this x. We're left with just h. So this was basically the average rate of change over the interval right here. So this is the interval, and this is the length of the interval, which is h units. Okay, so the average rate of change is basically you connect the endpoints of the intervals and with the linear line, and the slope of this linear line represents the average rate of change over this interval for this particular graph. Now, how do we go from this average rate of change to instantaneous rate of change? So here we go. We're gonna have to draw again, just just to make it simple. So we have a nonlinear function. It's not a straight line, it's just kind of curved. Let me see if I can draw a little better. This is with a better curvature. So we have it. Here we go. It's a little better. All right. So we're going to mark 2 points. This is first point. This is second point. Okay. So here we go. This is our x. And this is our x plus h. Okay. Now, the length of the interval is h units, right? This is h. All right. Now, when we go from an average rate of change to instantaneous rate of change, what we do is we try to reduce the interval size. So we're going to make interval smaller and smaller. It's going to shrink. And at one point, the interval, the h is going to become so small. It's going to be so small that your x and x plus h is going to be very, very close to each other, to the point that the line that connects these 2 points is going to become almost that tangent line just touching this point right here. So I'm going to go ahead and draw a few points just to show that the interval is shrinking. So now the new interval becomes, so if this is our x plus h value, so you know our interval has become smaller, this red dotted line, this is our seg. When we're reducing the, so reducing the h, the interval size, I'm sorry, so our points are coming closer towards your x. So I'm going to put another one. This is going to be a blue line. This is not blue, I'm sorry. This is green. So we have a little more contrast there, right here. So if you see this right here, you go that. This is your new x value. So the interval size is now just right here, this green line, h. Your new h is smaller. And now I'm going to use another color. This would be light blue, just to show you that the interval is shrinking. Okay, so now the new interval is like very, you know, this is the h value. So what I'm trying to show is that this, the h is becoming smaller and smaller, so we're moving towards this particular point right here, x. Okay, so okay, so what happens when h is really, really small, like really small? So the difference between x and x plus h is really like negligible. So the line that connects these 2 points, right? The line that connects these 2 points becomes almost like a tangent line to this point right here. Okay, when x and x plus h are so small, the line that connects these 2 points almost becomes a tangent line. So this tangent line represents the instantaneous rate of change at x. So this is what instantaneous rate of change is. When h becomes very small, goes to 0, then the slope m equals f of x plus h minus f of x over h. So this was basically the slope that we, the formula that we calculated for average line. So h becomes very, very small. So then this whole thing becomes from an average rate of change to instantaneous rate of change. Instantaneous rate of change. All right, so I'm sorry, hold on. So as h becomes very small, close to 0, so the average rate becomes instantaneous rate of change. Okay, so h is really, really small, and average rate of change becomes instantaneous rate of change. So this right here, the line becomes a tangent to point x, and the slope of this line represents the instantaneous rate of change at x. So this particular tangent line slope is the instantaneous rate of change. So as our interval size shrinks to almost 0, this becomes the instantaneous rate of change. Okay, I'm not this is just like kind of the mechanism that is involved when you define a derivative. So this is like one part of the derivative that's going to be discussed later on, but there are some other conditions for a function to meet, for it to have to be differentiable at a certain point and stuff like that. We're not talking about that. I'm just trying to show you the mechanism involved finding a derivative of a function. Okay, so from an average rate of change to instantaneous rate of change, basically the interval size has to become smaller and smaller, infinitesimally smaller, that's the word, I think, and then the average rate of change becomes the instantaneous rate of change, or the average at the slope of the average line, the interval line that connects the 2 points becomes like a tangent line to the point at x, and this becomes the instantaneous rate of change. So hopefully it's not confusing. Hopefully it would help you guys out. I think it would be a good starting point to go over these two videos, and that would help you to understand derivatives better.